All right. 305, maybe some. I said 405, but I meant 305. I got two numbers correct.
Over under 9.
So there's sample problems that you can read through on page 305, but we want to turn to, I thought that was an actual problem. Let's do a practice problem on 306, okay? So this, again, is one of those aspects to where with these two practice problems, you're not always going to be given the exact information as far as a balanced chemical reaction is concerned, okay? So, the first practice problem would pertain to farmers, okay? Because we're talking about ammonia. And practice problem 306. Ammonia, or NH3, is widely used as a fertilizer in many household cleaners, and in many household cleaners. How many moles of ammonia are produced when 6 mole of hydrogen gas react with an excess of nitrogen gas? Okay, so first thing you might think about, where's probably the first human mistake, well, I shouldn't say human mistake, but error that could be made in this reaction. They don't give it to you. You have to come up with your balanced chemical reaction. So if we have hydrogen reacting with nitrogen, where do you think human nature might let you down? Okay, so then the next part that you need to do is what with that reaction? Okay, so these are odd, these come in pairs, so you have to get this up to an even number. So in order to do that is put a 2 here. So that gives you 6 hydrogens to only 2. So we got to get this up to a 6, therefore we put a 3 there. Okay, so in this case, this is, I like to tell from one class to the next, year after year. See, I get to cheat. I can do this. This is what we're heading towards. Okay, so we are given an amount of substance. This is how I would suggest that you do these problems. It says you've got 6 moles of hydrogen gas. So this is what we've got. Okay, so it's asking how many moles of ammonia are produced. So it's an unknown value, so put X amount of moles and then a question mark. Now, you don't have to do it that way, but for instance, as you can already tell, if some of you have good hearing, this has buzzed a couple times where some of you, if you're in the middle of doing a problem, okay, if you don't write this down, you might get interrupted, but I think you would start over reading the problem, saying, okay, we've got 6 moles of hydrogen. Now we're looking for, oh yeah, now we've got how many moles of ammonia are going to be produced. Okay? There's only one place you can start. That's with your moles of hydrogen. And how many is that? We've got 6 moles of hydrogen. Okay? Now, it's always a good idea to put that 2 behind there, and it's always a good idea to do this labeling, especially this 2. And this is how I would possibly go about explaining this. Let's say it's in the first or second quarter in a basketball game. There's a made shot or made free throw. You call timeout. Okay? So since it's a made shot, when you come back out of that timeout, what's the official going to tell you? He's going to go like this. What is he doing? He's saying that you can run along the baseline because it was a made shot. But you're probably not having anybody guard you in the first or second quarter. Would that sound logical? So why is that official doing this when there's no one standing in front of you if you take the ball out of bounds? So when you get to the fourth quarter or overtime, if you keep that as a good habit or good practice, if you do this by habit, you're going to remember to do that in a game time situation. Because otherwise, and I'm sure it's happened before, maybe the official forgot to do that, and then the coach might say, run along the baseline. Well, the official should have done that already. But there again, it's just human error that causes that. Okay, just like human error with some of the camera angles they had on there. I could have swore that was a three-pointer that you made. Your foot must have just been on the line.
My foot was on the line, but they called it a 3.
Oh, they did? I thought it was the other way around.
No, it wasn't a 3, but they counted it as a 3.
Okay. All right, well.
No, my foot was on the line. I went back and looked at it because the announcer was like, a long 2, whatever, and they was like, oh, he's calling it a 3. It wasn't.
But see, you can't, there's no replay. You can't go, you could see it on there, but
at the game, you know how that could have gone?
should that have been called 2 points, it would have been 57-56 then as a final. How many people might know that other than,
What?
how many people might know that other than,
Howard dad told me that.
okay.
Well, I honestly kind of thought it was a 2 when I shot it, but then I went back and looked at it right after the game on that.
Okay. So again, it's just good practice to do that. So when the time comes, you're always prepared for that. I always think that's a good idea because some of you, it's just going to be human nature again. Some of you are going to do this, or you might not even put moles on there. How do you know how to cancel out your next step if that's all that you have? This is just a 2-step problem. What are we starting with? Hydrogen. But we need to get to what? Okay? The only way you can change substances on here is with that mole ratio. Okay? When you have that, that means you have a mole on the top and you've got a mole on the bottom. That's a ratio. Again, just like you shot 5 free throws, you made 4. That's a ratio. 4 out of 5. What, 80%? Yeah. Okay? So in this case, to me, if you don't label this, you're going to just confuse yourself with the further we get with these problems. But you label this as we go, H2 here. How do you cancel out H2 in your second step? You put that on the bottom. Now, should you put the coefficients in right away? That's fine. But what we typically do in here, until you get a lot better at this, is write your moles in here first, then go back to your coefficients. Okay? So we've got a mole to mole ratio, which means we got to look back at our balanced chemical reaction, and any of them large numbers have to go in front of the compound. So is there anything in front of hydrogen? Is there anything in front of ammonia? 6 times 2 divided by 3. So that's where that 4 moles is coming from. Okay? So once, and then also if you have it labeled like this, once you get to the moles of what it is you're looking for, you know that you're done. Because another aspect could be how many grams of ammonia are produced. Well, the only way you're changing that is this. Then you're putting grams on there. Now you know you're not done in this step. You have to put on one more.
Multiply it by the atomic.
Right. Mass. Yeah. So then you'd have to put moles of ammonia down here, and then the atomic masses of all the ammonia atoms up top. Yep. Simple problem. Do you feel it's worth your time to do practice problem number 2? Yes. Okay? So, here again, the decomposition. What does that tell you is happening? Just with those 2 words, decomposition. You're breaking it apart. Potassium chlorate, or KClO3, is used as a source of oxygen in the laboratory. How many moles of potassium chlorate are needed to produce 15 moles of oxygen gas? Okay. So you are not given the chemical reaction. So there's only one place for you to start, and that is with potassium chlorate, or KClO3. You probably can't see that. Okay, so KClO3. So if we're going to decompose that, I'll give you a little bit of a clue. What do you think might be left over? Yep, potassium chloride. Wouldn't expect you to know that. That's why we're working on that together. Okay? So the next thing that you have to do, we got a chemical reaction. What must we do next? We need to balance it. Okay? Just like we did up there. This is odd. This is even. So we got to get this up to an even number. So we multiply by 2, distribute that through the entire compound. But that gives us 6 oxygens. We've only got 2 of them here, so we need 3. Okay?
Is it alright if you put the O2 last?
Yeah, that's fine. That is correct. You can flip-flop. You can put potassium chloride, then oxygen, whichever. Okay? Now that you've got your balanced chemical reaction, it says, okay, you've got 15 moles of hydrogen gas. Did I say hydrogen? I meant to say, I was seeing if anybody's paying attention. Okay? So we know that we need to produce 15 moles of this. So therefore, again, it's asking the problem, how many moles of potassium chlorate are needed? So we don't know, so we put an X amount of moles on top of this. So we know where it is we're starting, and we know where it is that we're going to. And again, I get to cheat. I'm going to put 10 up there. Okay? Do you want to try this on your own, or do we work on this together? Okay? So where's the only place that we can start? With your 15. That's the only given information that you have. 15 mole of oxygen gas. Okay? 2-step problem. How do we cancel moles of oxygen on our second step? Okay? So for every mole of O2, we get a mole of potassium chlorate. We've got a mole ratio. We've got to go back to our chemical reaction. Okay? We've got to put a 2 here and a 3 there. 15 times 2 divided by 3, 10. We're just do what part now?
So like to balance it, you put 3 oxygens, so that's why where you get the 3 moles.
Yeah, from right here.
Okay.
Yep, that is correct. Now, is this being too precise? I don't think so. The reason we're spending so much time on this is because some of you are going to see this again in 2 years, 3 years. Okay? I'm only telling you now because you're going to probably be asked this same amount of content. This is free. This is free knowledge. Okay? Next time you see this, it's probably, we'll say, about $650 worth. Okay? So I believe it's probably somewhere around maybe, that might be a little steep, but I want to say it's $110 a credit maybe. And it's probably a 5 credit class.
It's 4.
Maybe, okay, so it's 4.
It's about $4.50.
Yeah. But yeah, just get your checkbook out, write it out, no problem, right? I don't even know, you can't overdraft anymore.
Yeah, you can.
You
I mean,
can?
You can't, but then you get like a fee, I think.
Okay. Okay.
What's the plan
Okay.
for tomorrow?
Just two. You going? Okay, that's fine. We'll probably be going over the next type of problems is amounts of moles to mass. So that's a 3-step
Will
problem.
you record it?
Yeah, just like I am right now.
Right on.
Yep. Okay. It's, again, we can go to a section review on here that would have mole to mole problems on there, or we can just make one up. You need to tell me what you think works for you. Left outside, are we good? Okay, middle and right side. Okay, so maybe we need to do something that's just a not so much difficult in the math, but maybe just something that's a little more difficult in the equation. Not saying we like to say that to be mean, but all right.
Certification.
Video.
Get them all shots.
Oh, right on.
Go get them none of the water.
Well, this won't be too bad, I don't think.
PQA or PQA certification. Gotta remove it.
Me?
Those little vials are done. She doesn't check on them. You already have it? Yeah, I do. Yeah, I do.
Did you get it recertified?
Yeah, I got it.
Okay, would you want this to be a mole to a mass problem or just a mole to a mole? The mole to mole is what we just did. Mole to mass is what we'll be going over tomorrow. Okay, does anyone else have any problems with that? Okay. And I believe this is pretty accurate. For some reason, when we're talking about microbiologists utilize this compound, bacteria doesn't like silver. You know, I like silver, so I guess I'm not a bacterium. So, yeah.
Well, that's good.
Yeah. Just helium. I guess that's just a gas, right? Yeah. Anyway, so moving forward then, if and oxygen react, which they probably would, provided you give it a catalyst, how many grams of so I need a number of moles. Don't do something like 3.89. Put it on a quarter, a half, or 3/4, or a whole number.
4.
Just 4? Okay.
4.5.
4.5. 4.25. Okay. Get in on this auction. I hear 5, 5, 5, 5. Anybody? 5, 5, 5, 5, 5 1/4, 5 1/4, 6, 6, 6. 6. Do I hear 7, 7, 7? 7 1/4, 7 1/4. Anybody? 7 1/4, 7 1/4, 7.
750.
750.
We're not
quarter.
bad.
We're not doing a quarter.
Maybe. Yeah. So I like that. Produced from 7.25 mole. Silver or oxygen? Okay, I heard silver. Okay. So we'll work through it together, but I want you to work on your reaction.
HgO2 is Hg plus O2.
Did you say HG?
Hg plus
I hope not.
As an apple.
Yeah, Ag.
Okay. See, I know I'm old, but my hearing isn't that bad. So.
Ag plus
Okay.
O2.
Yeah,
That how you start it.
yeah, that's correct.
Okay, wait. Okay, never mind.
This is how you do things back in the homeland?
I don't even remember how I
Oh, okay. But this is fun. You can lie to me, you know. Just say, yeah, this is fun. Oh, this is awesome then. All right. Okay. Chemistry is better than biology? I think so.
I got 412.
Okay, so we're kind of, it's not that we're running low on time, but if we're taking some silver, okay, the first trap is probably going to be what? Some people, you think I'm making this up. Some people, from human nature, you're going to make this mistake. But just like every time we say this, two things. Okay? Try to learn from them, and if you learn from them, you hopefully won't repeat them. Okay, so then what does that give you then? Well, there it is, Ag2O. Why is there two silvers? A +1, and oxide or oxygen has -2, so you have to have two of those. Okay, so with that being said, we've got two oxygens and only one over here. Agreed? Okay, so now, how do we start this problem? What are we beginning with? Okay, so 7.25 moles of this substance, and we want to know how many grams of this will be produced. Now, something, to me, this would be a practical answer because not all bandages are the same size, are they? So logic would tell you the larger the bandage, probably the more of this you're going to have to add. Because if you have a bandage that is, we'll say, this size, but you only put enough silver in there that will make a bandage this size. Could that be a potential problem? Yes, because what do we say? Why are microbiologists utilizing this compound? Because silver repels what? Bacteria. That's right. So it's going to be a bad day at the office if you run yourself short on this silver. Okay. So now we've got 7.25. Okay. So this is a three-step problem, so it's just a little longer. How do we get rid of that mole in our next step? Okay, so for every mole of silver, this will allow us to get to this side of the reaction because of what ratio? What ratio?
I also got synthesis.
What ratio?
2 to 1.
What ratio?
1 to 1.
No. The definition of what this step is called.
3.625.
Say that again. No. Well, those are the numbers. What's that called, though?
1 to 1.
Say that again. Mole ratio. The mole ratio allows you to change what you have into what it is that you are looking for. Okay? So now, oh yeah.
Yeah, but
I was just seeing if you're paying attention.
does that even matter though?
Yes.
Yes, it will. This, it'll really matter. Okay, so what goes down here? Why, we're not making this up. Where does that 4 come from? Right here. Is there anything in front of here?
2.
Okay? So these have canceled out. Now you are in moles of silver oxide.
3.625.
So we want to cancel this out. So then what would go up on top? So what is it? 107 and 16 gives you,
231.74.
okay, so 231. I'm just going to say 231. Now, this is going to happen too. This is just human nature.
You have to do the first one.
Some people might do that. Why might they make that mistake? Because they're looking at this. The only time you put coefficients in is when?
We're trying to cancel moles.
When you have a mole to mole ratio. That's the only time you look up here. Okay? You do not put anything in front of here. Otherwise you're going to be off by a factor of 2. Okay? So 7 1/4 times 2 times 231 divided by 4 gives you 837.
I got like 840, but I did the
Okay, but you put the point,
0.7.
dot. Okay, that's fine. But to me, in my estimation, just like another class is going through, you always know on that slide rule where you're at when you utilize this periodic table. You always know where you're at in this problem if you keep labeling the work as you go. Make sense? All right, we'll catch up to you next time.